Okay, boys and girls, welcome to our 5th video lesson, Chapter 10, our continuing saga and exploration and quest for understanding and domination of circles. Alright, let's do it. Okay, let's look at our first theorem in this chapter section. It says, in a plane, a line is tangent to a circle if and only if, and again, that if and only if means that this theorem works both ways. The theorem works and the converse of the theorem also works. So, in a plane, a line is tangent to a circle. If that is true, then it is perp to a radius drawn to the point of tangency. So a tangent line to a circle is a line that touches the circle at just one point, here at point T. Okay, which means now if this is a tangent line at point T, then a radius drawn to that point of tangency is a right angle. And also, if I draw a radius to a line of tangency that is a right angle, therefore now where it hits this tangent line must be the point of tangency. So if ST is drawn perp to line L, which is a tangent line, this point T must be a point of tangency. Okay, our next theorem says if two segments from the same exterior point are tangent to a circle, then they are congruent. What that says in English is that if I have a point outside my circle, let's call it point B, and I draw two lines of tangency to the circle, these two lines are both tangent to the circle, which means they just touch at one point at A and at C. If those two tangent lines are both drawn from the same point B, then these two tangent lines are congruent. And we also now know if I draw the radii from D to point C at the point of tangency, and from D to point A, the point of tangency, those are going to be right angles from the last theorem. Okay, let's move on. So, find the missing side. This is a famous walkabout problem. Smiley face, smiley face. So, I'm just going to look here. I want to find the missing side. That would be this side right here. And now I'm going to do a bunch of labeling. Okay, I know from the two tangent theorem that we just talked about, this point right here. Okay, I know that my circle is inscribed in my quadrilateral. Therefore, this piece right here must be congruent to this piece because those are both tangents drawn from the same point. Likewise, in red, this piece must be congruent to this piece. Likewise, in blue, this piece must be congruent to this piece. And finally, likewise in green, this piece must be congruent to this piece because all of those corner segments are drawn from a common point of tangency, or a common point to the circle, and they are all congruent by the two tangent theorem. Okay, so let me just go back and make sure that is red, right? Yes. Okay, which means now I just need to start somewhere on my circle and start walking about, and it really doesn't matter where. So I'm just going to choose, I don't know, in green, I'm going to choose this piece right here and call it X. If this piece is X, therefore now this piece right here in green is also X, because those are equal. This piece right here in blue must be 20 minus X, because this total length right here is 20, and this is X, so this is going to be 20 minus X, which means this piece right here is also 20 minus X. Okay, I'm going to go up here to purple. Actually, I'm going to go up here to orange. That's what I meant to say. There ain't no purple on my picture. Okay, if this piece right here is X, right? This piece right here must be 18 minus X. That's this piece right here. Likewise, this piece right here must be 18 minus X. Now let's find the length of red. This is interesting. This red piece right here, I know is 24 minus this orange piece right here. So that red piece is 24 minus the orange piece, which was 18 minus x. So if I distribute my neg, I get 24 minus 18 plus x. So this piece right here is 24 minus 18, which is 6 plus x, which means this piece right here in red is also 6 plus x, which means now this total length of my missing side, this length right here, is 6 plus x plus 20 minus x. What? Let's write that out. 6 plus x plus 20 minus x. Well, 6 plus 20, that's easy. That's 26. Plus x and minus x, well, that's nothing. So my final answer is 26. Cool problem. Okay, we will do a few more of these in class, but I wanted you to have one on file so that if you ever needed to go back and look at one, you can. Okay, and we can do this both with the circle, both inscribed and circumscribed about the quadrilateral. But we'll do more in class, I promise. Okay, next I'm going to we're going to outline a quick little procedure called the common tangent procedure. It's a recipe. You're going to follow this recipe when you do these next type of problems. These are kind of tough. I'm going to do a couple for you right now, but we will also do some in class. But your steps are this. You're going to draw a segment joining the centers. You're going to draw the radii to the points of contact, and this will make sense as we do it. Here's the hard part. Through the center of the smaller circle, we're going to draw a line parallel to the common tangent that intersects the radius of the larger circle. I know that's a mouthful, but we'll do a couple. And then we're going to use the Pythagorean theorem to find the missing sides. So, okay, let's do this problem right here. We have a common external tangent. That's this line right here. That's a common external tangent because it's outside of the circles. And it is 12 inches, so I'm going to write that in here in pupil. That's 12. Okay, I have radii of 8 and 3. So that's 8, and this is 3. How far apart are the centers of the circles? And I'll draw that in orange. That's going to be this line right here, and this is actually the first step in our series of steps, our recipe to solving these problems. We have to draw that line called the center line. Okay, and that's what we're looking for. We're looking for the length of that center line, so we'll call that x. And that was, as I said, step 1 in our recipe of solving these common tangent problems. So let's continue. Let's do step 2. Let's draw our radii from the centers of the circles to the points of tangency. I'm going to label each of those. Okay, this guy is 8, and this guy is 3. Okay, let's just mark these as right angles right here because we know that a line drawn from or a radius drawn to a tangent line to the point of tangency makes right angles. So now that being said, let's do our step 3, our third step, which can be the hardest step. Through the center of the smaller circle, we're going to draw a line that is parallel to our common tangent. So there it is, and then that line must pass through the radius of the larger circle. So this line is parallel to the common tangent, which means now these lines are parallel right here. These are right angles. These are right angles. Well, a line that's perp to one of two parallel lines must be perp to the other. So these are all right angles right here, which means now I have a rectangle right here. And I also have a right triangle. That's a right angle too. So I have a right triangle right here. That's a right triangle with my right angle being there in the upper left-hand corner. So now let's just use our properties of rectangles. If this side is 12, well, then that means that this side is 12. And if this side is 3, that means that this side is 3 as well, which means now this remaining piece must be 5. So as we're looking right here, I have a right triangle. Here's my right triangle with one leg of 5, one leg of 12, Hey, ding, 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 ding. The third side here, the hypotenuse must be 13. So the answer to my problem is the length of my line of center is 13. Okay, let's do one last problem. This problem is also a common tangent problem, but this time our common tangent is an internal common tangent because it goes between the two circles. Okay, we already have our line of center drawn. It has a length of 20. It says it's 20 up here. Okay, and our radii of the smaller circle is 5. The radii of the radius of the larger circle is 10. We want to know what is the length of the common internal tangent, meaning from this piece to this piece right here. We want to know what that length is. So let's just follow our steps right now. Step 1 is done. Our common line of center, our line of center is 20. I'll just label that right now. Our radii, okay, our step 2 is draw our radii to the points of tangency. So this guy right here, and that of course is a right angle. That has a length of 10. This guy right here, that of course is a right angle as well. It has a length of 5. And now we're going to do the hard part, step 3. Through the line of, through the center of our smaller circle, we're going to draw a line that is parallel to our common tangent. And it must pass through the radius of the larger circle. And we see now that line that's parallel to our common tangent does not pass through the radius. So we're going to extend the radius just like that. Okay, and now what I have, once again, is I have both a right triangle and a rectangle. My rectangle is right here. Remember, these two lines were parallel right here. These two lines were parallel, and these are all right angles. Okay, so I have a rectangle right here, and I have a right triangle right here, because this is a right angle right here. So I have a right triangle right here. Okay, let's fill in some values. Well, if this length is 10 and this length is 5, because this length is 5, that means that this length is 15. This length right here is actually the hypotenuse of my right triangle. And this length right here, I can call x. So I have a right triangle that looks like this. We want to say it's a 3, 4, 5 times 5, but it's not because I see the 15 and the 20. The 20 is actually the hypotenuse. This is 15 and this is x. So we need to solve that for x. So I know that x squared plus 15 squared is equal to 20 squared. Well, 15 squared is 225. And 20 squared is 400. Subtract the 225 from both sides. X squared is equal to 175. So x, I'm going to keep writing up here, is equal to square root 175. We know that 175 is 25 times 7. So x equals square root of 25 times 7. So x is equal to 5 root 7, because we know now that I can pull my 25 out and he becomes a 5. So this is 5, and root 7 is still left inside. So x is 5 root 7. And notice that this length is going to be the same as this length, because they are opposite sides of a rectangle. So the answer to my question now is, how long is this common tangent? It is 5 root 7. All right, hey, that's it. We'll see you soon. Have a great day.